Hey everybody, what's up? I'm here with another Unity tutorial in a short period of time this time. I'm starting to get better at making videos and starting to try to make a little bit more time. So I figured I would do another one on cameras since that one came up in some comments. And since I already had a project made for myself as a little test project, I figured I'd use that as the example. And so here I am, and today I'm going to present a tutorial on the follow camera, or on a follow camera, a kind of follow camera. And this one is just something I designed for myself, for my own purposes. I wasn't trying to solve any problems. I was just thinking about this on my own as if I were trying to make a game with this kind of camera, and I came up with something that maybe has been done before. I'm sure it has. I didn't really refer to anyone else's version of this. I just tried to come up with something for myself, and so I'm going to walk everybody through this. And this one has some code in it, which I think might be useful. And again, it leverages some of the lessons that I went over in a previous tutorial, so it might be helpful to piece everything together. So this tutorial again is about using a follow camera, and I have a scene set up where say it's a fantasy RPG style game where you have multiple characters and you want to follow one of them around, and you also want to be able to switch the camera to follow a different player around, and in some occasions you want the camera to track two different characters and have them both be in the frame of the camera so that it's obvious that the two characters are interacting with each other. And one more goal is to have the camera avoid occluding with the environment, either by avoiding collision with the environment or just going through the environment, through walls, through roofs, through fences, whatever, but also turning that material transparent so that you can see that there's something in the way, but it doesn't obstruct your view. And I'm sure you've seen this in many games in the past. So I also wanted to mention that Unity has a new camera system called Cinemachine, which seems to provide support for this built in. And I am not going to claim that this is better than that. The purpose of this isn't necessarily to just give you a paint by numbers off the shelf, just take it and run with it, put it in your game kind of thing. This is more about a tutorial that helps you understand how cameras work, how the math works, and how the logic works, so that if you do end up using Cinemachine and ignoring all of this, at least you'll know how it was done, and if you ever need to do anything custom yourself, you'll at least have some better understanding of the underlying work that goes into the camera system. So that's kind of the purpose of this. I'm not trying to give you something that you can just take and use right away. If that's something you're looking for, then maybe you're not interested in this kind of tutorial. But if you are curious or interested in how the math and the logic works, then this is the right place for you. All right, so without any further delay, let's get into what I have in my project, and I will first take you through the script that I wrote. Okay, so here we are inside a familiar Unity scene. I have my camera over here, and here's a completely made up town that I'm using as my example environment. And I've got what I call town guys, are these I guess built-in Unity characters that are kind of in the T-pose right now, and they're just placeholders. I'm using them as my town characters. So don't worry so much about what they look like, or how they behave even. Just know that these are guys that are used as the characters. So back to the camera. And right now it starts in a default position, which is kind of outside the city, outside the town, pointed down, not really looking at anything in particular. And that's kind of on purpose because I don't really want to start off just looking right at a character, because you never know where your characters are going to be. So it's better to have it handle any situation, and the default one is to have it looking kind of just down at an arbitrary angle. Now, again, the goal is to have the camera track a character. So let me briefly go over some of the parameters to my camera follow target script here. The first parameter is who should it follow, and this is going to change during the script's execution, but it's just sort of like a default. Who do I start looking at? Who's the first thing I'm going to look at? The minimum distance here is in units. How far away should the camera be, but never closer than this? So basically, it's never going to be any closer than 15 units away. So it's going to keep its distance, in other words. Speed is an arbitrary value. I don't even know what the units are really. It's just a number. If I want it to go faster, I make the number bigger. If I want it to go slower, I make it smaller. That's all it is. So I don't really remember the units, but it's not that important. Same with this one. I think maybe it's in radians per second or something, but it again, doesn't really matter. If you don't like the number, you just change it until you like it. I'll show you how the math works for both of these. Random target is just a boolean that says whether or not it should pick a random target or whether it should just stay on this guy. And this is sort of a helper member, not really important to the tutorial. It's just what's the material that I'm using for making things transparent. Right now, only wood can be transparent. Again, not a graphics tutorial, so let's not get too hung up on that. Occlusion radius is not used, but I have it here anyway just because it's something you can easily add in there and tune yourself. What I ended up using for occlusion is the capsule collider that the camera is attached to. Okay, so let's watch what happens when I play this scene. So here I'll unpause. So camera pans smoothly to our first character who's now working, and he's continuing to work, and for as long as he's there, the camera is focused on him. And now he goes to idle and starts walking to a new location. Camera pans smoothly, follows him around, make sure that he's in view. But you'll notice it's very smooth, and there's a little bit of delay between the character's movement and the camera moving to follow him to keep things from being too jarring. So here the characters are now engaged in conversation, and the camera pans to focus on this character and this character who are now talking to each other. And don't worry about this guy, he's just in the background. But you'll notice that these two characters are in view, and the camera is taking a spot that's essentially perpendicular to this line that joins the two characters. So if you drew a straight line from here to here, and then a perpendicular line, you would have where the camera is right now. And that helps to keep the camera focused on the two characters. So they're talking to each other, and they're going to wave to each other here. They say goodbye, camera switches to this single character, and now is following him. And right now I've got some occlusion issues right now where not everything becomes transparent, but that's easily fixed with some tuning. So the camera continues to pan to track characters, and that's basically what happens here. So one of the things that you'll notice is that all the camera movements are smooth and not snapping to any particular spot. The camera knows it needs to target a character or a new character, and instead of jumping there, it sets that as the goal. And for as long as that's the goal, the camera will move slowly towards that goal. And the further away from the goal the camera is, the faster it will go. And as it gets closer, it slows down. All right, so here's another example. This time I have a yellow line that shows you the perpendicular line of where the camera should be. So this is its target here, this blue point. And this yellow point, which is kind of inside the building, is going to be its point where it wants to be. The camera wants to be at this yellow point, and the camera wants to be looking at this blue point. So here it is trying to settle into place, and as it's doing that, it's making everything become transparent so it can see through the building. And so that's what it's looking at, through the building. And it seems to work. This isn't ideal, it's not perfect, it would need some tuning, but you get the idea. Alright, so here's the fun part. We are now going to talk about the CamFollowTarget script. So I explained the parameters already. These are them here. Again, occlusion radius we are not using. And there's some private variables here. I'm not going to get too much into those. So the first thing I want to do is go through the FollowTarget function. That's this one right here. So the first thing this does is we're going to get a difference vector between the current camera position and the follow target position. So if you remember a previous tutorial, difference vector is kind of like a line between the two. So the target is this position here, and our position, because this script is attached to the camera, so the transform position is this object's position, which is the camera. So the difference between the target position and the transform position goes into diff. So here we have the difference vector being given to the look rotation function, which basically turns a difference vector into a quaternion. So the quaternion will store that rotation in that direction, and when you apply that to something, it makes it point in that direction. Okay, then we're using the angle function to get the difference between our current rotation and the one we want to eventually be at. So that's this angle. That returns us an angle. That's just a scalar value. So now we're getting into some more advanced math here. Not too complicated, but hopefully you'll be able to follow me here. So I like the inverse lerp function. What this function does is, think of it this way. If you take this value A and this value B, and you give it a third value C, it's going to tell you how much in between this and this value is. So C is how far between 10 and 180. So when I use it here in this next function, I have a number between 0 and 1 that I'm using here. I'm kind of going the other way around. So what I'm saying here is that I want this value, this speed lerp, to be whatever the distance between this angle was, between these two values was. I want this value to be the same. So a couple quick things. Rot lerp is going to be a value between 0 and 1. The result of this function is only ever going to be a value between 0 and 1. If angle is 10, this value is 0. If angle is 180, this value is 1. If angle is 190, this value is still 1. And if angle is 0, this value is 0. So beyond, if it's 10 or less, it's 0. If it's 180 or more, it's 1. And everything in between. So if it's halfway between 10 and 180, which I guess would be 190 divided by 2, then that would be 0.5. Then this value would be 0.5. So that's the important thing to keep in mind. And because lerp takes a value between 0 and 1 and goes the other direction, then when this is 0, you get this value. And when this is 1, you get this value. What this ends up doing is saying that the more the camera rotates in degrees, the faster it should rotate. So it's basically a way of speeding up and slowing down the rotation. The closer it is towards its goal, the slower it's going to get. And that's what I want. So here we are actually setting the camera's transform rotation. By using rotate towards, we're not immediately setting it to our final rotation. We want it to slowly get to final rotation. In order to do that, we tell it rotate towards wherever you are already, and this is your final rotation, but we only want you to go this fast every frame. So that's what's happening here. It's going to slowly rotate towards, or maybe quickly rotate towards, its final rotation. And obviously, if you just set rotation to this, it would snap there, and that's going to be very jarring, and you don't want the user to have to deal with that headache-inducing thing. So the next step here is to basically overwrite diff. We've used it once, we're just going to use it again. We're overwriting it, we're not trying to create a new variable. I don't know, I do this sometimes. I don't think it's you know, it's not really necessary, but just reusing a variable. So I'm getting the xz difference between where we want to go in terms of our position now. So we've done with the rotation. This whole section here was rotation. Now we're going to do position. And if you remember from one of my previous videos, xz leaves out the y component of any vector. It's just the x and z components. So basically snapping everything to the floor, and because we don't want to deal with any heights. That can confuse some calculations that, since vectors are 3D, but not most of the time, but occasionally you want your vectors to be basically 2D projections from the to eliminate the y out of the vector. So basically, like if you were to shine a light directly above any vector in 3D space, the projected shadow on the ground would be the xz version of that vector. And again, previous videos I've showed that why we're using the square of the magnitude and not the magnitude. Again, that's for efficiency. We don't need to compare doing the square root to get the magnitude can be slow. And even if it isn't slow, it's just something that I've gotten in the habit of doing, and you don't really need to do the square root to get a comparison. And so because we're only comparing the squares, we're doing it more efficiently. Let's see. So, and the reason I'm doing that is that I can figure out if we're moving the camera backwards or not. So this is basically saying if the distance between our position and our position here and the target is less than a certain minimum distance, which I have up here. Minimum distance squared is our minimum distance, but squared. Just to do it more efficiently, we store it in a variable rather than calculate the square every time. I can't help it. I'm probably optimizing more than necessary, but that's just the way I'm used to doing it. The min distance is what was passed in. So we're going backwards if our distance is less than the minimum distance. We need to back up, basically. We're too close. So close enough is just a calculation where if the distance between where we want to go and where we are right now is less than a certain minimum, then we're close enough to where we want to be, and that's where we exit the function. So this is something that if you don't have this, you could end up continuously moving the camera, and sometimes you get into this ping pong where you go a little bit past the destination and then you back up and you go a little bit past in the other direction, and you just get this back and forth motion, and that looks really, really bad. So this is where this close enough calculation comes in. And this last bit here was before I had my xz extension method to the vector, which I actually used up here, and I'm just realizing that I didn't use it down there. But this xz extension is basically the same thing here. I created a new vector, zeroed out the y, and that's the one I'm using to move the camera. So all of this calculation up here was just so that I could have a value to move the camera's position. So it is going to increment by whatever forward is and however long the forward increment is. Alright, so that was a lot of math dealing with rotation and translation of a camera. Hopefully not too complicated, especially if you watched some of the other videos that I created. I did my best to try to address the same techniques that I used there, but I added a few new ones in for this one. But hopefully you can understand now why it's so important to understand difference vectors, position vectors, and how doing any of this would be pretty much impossible if you didn't understand that fundamental concept. So carrying forward with this, the move to desired position function is used when we are engaging in dialogue between two characters. So this one's only used for the cases where we have two characters that are talking to each other and we wanted to frame them, if you remember what that looked like. So this is the function that moves the camera to the position that's perpendicular to the line that you draw between the two characters when they're facing each other. So in order to do that, there's actually less code here. which is interesting, but it's a similar concept. There's only one additional piece to this that's very important and something that will be used quite a bit in 3D game programming. So the position we want to move to is, this is a difference vector. So it's where our desired position is in our current position. So the x, using xz again, so we just want to do it based on just on the ground, the difference between where we are and where we want to go. And this, again, this assumes we have a desired position already figured out. Alright, so here's the code that we are using to figure out where the camera should go when two players are talking to each other. So first thing we're doing is we're picking one of the two players. Doesn't matter, but whichever player of the two we pick, if he's talking, then let's figure out where he is. And again, we're using xz. We're going to use xz for pretty much all of this. Then we want to find out a difference vector between this guy and his talking partner's position. So that's that line that's drawn between the two characters that are talking. And then the critical piece is getting the cross product here. So the cross product is used to get a vector that is perpendicular to two other vectors. The two vectors that we're using here are the vector we just figured out, the line between the two characters, and the up vector. So if you imagine what this looks like, so this is our scene, and I'll just use these axes as the example of the cross product of what's happening. So if this red line is the line between the two characters, and this up vector is pointing straight up, then the cross product is this blue one. That's how the math works. If you give it two vectors, the cross product gives you a third one in a completely orthogonal direction to the other two. So you've probably seen, maybe you've seen how to calculate the normals of a quad or a polygon. You need to take two vectors, and the third vector of the cross product is the one that's pointing straight out of those two. So essentially we're getting, if this green line, well, actually, let's look at this. It's this blue square right here. That is the square formed between this green line and this red line. There's a blue square right here. And a vector that's pointing straight out of it, let's say it would be its normal, is the cross product, the result of the cross product. So we get a perpendicular line exactly perpendicular to these two vectors. So back here, once we've got our cross product, we have a perpendicular vector. And then we can first normalize that, make sure it's a unit vector. And we scale it by how far we want the camera to be away, the minimum distance. So that's where we don't want it 1 unit away, we want it this many units away. So that's why we normalize it and then we scale it up to that distance. And that gives us basically our destination point. And so that's where I draw that line. Now, another interesting calculation here is, remember the center vector is the difference between the one character and his partner. When you scale it by 0.5, you're taking a point that's halfway between the two. If you looked at my previous tutorial on vectors, you would see when you scale a vector by 0.5, you basically cut it in half. And so if you take a vector between two characters and you cut it in half, you get the center point between the two characters. So that's what this center is. Okay, so in order to demonstrate what's happening with this calculation right here, which is sort of like the culmination of everything that we've learned up till this point, I'm going to go back to our Unity scene and try to explain it there. So keep in mind we're adding 3 different vectors. And just like in the original tutorial, you've got a difference vector, you've got a position, and you've got a direction vector that's been scaled. So you have all three types of vectors all at the same time. So that's why this is so confusing to people who don't understand the differences between the different vector types. Essentially, they're being all added together, and that seems simple enough, but why? That doesn't quite register. So let's go back to Unity and maybe this will make sense. So remember, townie position is the position of the first character that we identified up here in the loop. So this guy, this first guy's position. Center was the difference vector that was halfway between the two characters, and cross was the perpendicular line that was basically pointing in the direction that we wanted the camera to go, but it's only a scaled direction vector. It doesn't have a position in 3D space. So just keep that all in mind. I'll come back to that in a second. Okay, so here we are. We've got character 1, character 2, center, point. So essentially all these calculations are to give us this yellow point. And you can only get a point when you at least start with a position of some kind. So otherwise your point is going to be from the origin, which 99% of the time nothing you ever do in the game is going to be at your actual game origin. So you have to get that position into the space that you're working with. So to get a point, you start with an actual 3D position vector. That's this magenta one. So that's a physical point in space. It's right here. When you add a difference vector to it, you take it and you essentially move that point along that difference vector to the end of that difference vector. So this difference vector started out as if you remember, it was a full difference between character 1 and character 2. Then we scaled it by half. That made it this long. So now we have a vector that is this long in this direction, but it's not in 3D space. The only way to get it into 3D space is to add it to a position vector. So we start with this position vector. Otherwise, this 3D vector right here would be originating at the origin. Again, everything that isn't added to a position vector is going to be from the origin. Okay, so we start with our position vector here, and we add our difference vector here to it. That gives us a new position vector, which is this blue point. And that's the point that we want the camera looking at, but it's not the point where we want the camera to actually be placed. So in order to get that value, which is the place where the camera should go, we need to take this position vector, it's a new position vector, and we want to add that to the cross difference vector that we had calculated earlier, and that moves the position from here to here. And again, adding a position vector to a difference vector gives you a new position vector at the end of that difference vector. So that moves the point up here, and that's exactly where we want it. So now we have the blue point and the yellow point, and those are the two key points for the rest of the script. So back to the script again, and our blue point is townie pos plus center, and that is exactly where we want the target of the camera to be. So we want our camera's target to be at that blue point. And here I am just adding a Y component to it because we don't want the target position to be on the ground. We want it to be 1.5 units above the ground. That's what this additional calculation is here. And just to clarify, the up vector is a direction vector scaled by 1.5 times. And this is a position, this is a difference vector, and this is a direction vector. So you've got all three different vector types here, but only one position vector. So you have a position added to a difference and a direction. And you end up with a new position vector, which is moved along this difference vector and also along this direction vector. So the result is a new position vector that is where we want it to be. So that's the blue position, the blue point. The yellow point is this desired position. So if you look at the yellow is the calculated camera position, and same thing. It's a position vector with a moved up by 1.5 units. Okay, so back to this part of the script, you can see where desired position and desired target are used, and it's basically the same code as in the previous script that I showed. The same math with inverse lerp and the lerp and the rotate towards. So it's pretty much the same stuff, and I'm not going to go over it again, but it should all make sense. And just note that the cam speed is what was referenced up here as one of the tunable parameters. So this is how you'd be able to tune the speed of the position translation. All right, so as this plays out again, I'm going to wrap things up here, and hopefully I explained how this type of camera system works, and maybe pointed out some things that maybe you weren't aware of. And hopefully you'll find this useful. So thanks again, and we'll see you on the next one.